So let's welcome Joe Fabbre from Green Health Software. His talk will be about software considerations for safety and security critical systems. Joe, what are the major safety and security critical systems issues in a car you're targeting?
Well, before we get into talking specifically about the safety and security systems, I think it's important to realize that a car is an incredibly complex system of systems. And so Green Hill's products are used in all different areas of the car. We've been around for 38 years. We started off as a compiler and a tool chain company. Our products are used in powertrain and body, in things like gateway modules in cars, ADAS systems, various other things like instrument clusters and IVI systems. So our products are used all over the car. I think in recent years, one of the most interesting problems facing the development of this complex ecosystem is designing high levels of safety with high levels of security. So ever since some of the hacks that we've seen happen in the last 5 or 6 years, Green Hills has really focused as a company on bringing technologies to market to help address both safety and security in some of the critical systems in the car. And so I think some of the obvious safety critical systems are things like ADAS systems, autonomous driving, computers that ultimately end up either sending commands to control or directly controlling steering, throttle, and brakes. Those are some of the more interesting systems. In terms of security, all of those systems are interesting, but because a lot of the entry points for the attacks that have happened on vehicles in recent years have been through the infotainment system, we've actually been investing quite a bit in our infotainment architecture and how to deal with the absolutely massive amounts of code that it takes to make up an infotainment system. And so I think we'll talk about some of those challenges as we go through the interview here.
So is this also then your major focus?
Yeah.
The infotainment system,
yes,
where you put most effort in.
Right, that's right.
And
it is infotainment, but it is autonomous driving. It is secure gateways. It's the telematics unit. It really is across all different areas of the car. The reason I picked infotainment is I think that's an interesting one for the security aspects.
Okay.
Yeah.
And how does your technology work in this context?
Well, I think if maybe we can advance through a few slides here. I wanted to point out that the reason that cybersecurity is so important in vehicles is that there are over 70 million vehicles produced each year. The software in these cars is replicated, so that software all ends up having the same flaws. And these flaws are the things that lead to security vulnerabilities in the system. So those flaws get deployed across hundreds of thousands or millions of units, and a single exploit has the capability to potentially simultaneously impact all of those units at the same time. And so, the other thing is if we look at the complexity of the software in a car today, we're talking about hundreds of millions of lines of code, and it's far more complex than things like the software that flies in the 787, or even the software that makes up Facebook today. The software that goes into a car is much more complex than that.
And how do you exactly address this problem? With patches like Microsoft does at the operating systems?
Well, a firmware over-the-air update system is a part of addressing that complexity, and it's a necessary part. But I don't believe it's the end-all, be-all. I think that actually designing for security from the ground up is more important. And so I'll get into that here in a couple of slides. But I wanted to address, so we've established that there's 100 million lines of code in modern complex vehicles.
Okay.
And if we take a look at, and I mentioned earlier, these vulnerabilities and a lot of the safety defects come from bugs in the code. And so if we look at some of the industry averages for things that are deployed in systems, we'll see on average there's between 1 and 25 bugs deployed in software per 1,000 lines of code. And if we look at other things like clean room development, which is the type of development used for space shuttle delivery, internal QA, you're at 3, shipped, you're at 0.1. Now, I mentioned also that vulnerabilities they are a subset of those bugs that are in the code. And if we look at some of the popular products, like Google Chrome has 0.06 vulnerabilities discovered per 1,000 lines of code. The Linux kernel has 0.04. OpenSSL, which is a security protocol, has 0.13. And the reason that I'm pointing out these numbers is that if we look at over 5 years in a modern automobile with 100 million lines of code, what that means is that we'll have 0.05. We'll use the conservative numbers from the previous slides. 0.05 discovered vulnerabilities and 0.15 undiscovered, but they're probably there. And what that means is that over a 5-year period, there will be 5,000 vulnerabilities discovered in this platform, and 15,000 that are probably there but were not discovered. So how do we address that problem? Getting back to the question you asked me a minute ago. I think it's very important that we have a technique to isolate those enormously complex pieces of code in the system from the safety and security critical pieces of code. And our Integrity Real-Time Operating System, which is the flagship product from Green Hill Software, was specifically designed to enable exactly that architecture. So it's something called a separation kernel, and you can apply a design technique called designing with the principle of least privilege. That's a very well-known to be effective security technique, where you take the security critical components and you apply a very rigorous software process. And then by having Integrity as this separation kernel underneath that, Integrity gives you two things. One, it gives you guaranteed separation of those security critical things from the non-critical things in your system. And the second thing is that it's been evaluated to an extremely rigorous level to show that it itself doesn't have any bugs in it that lead to security vulnerabilities. So with those two things, you now have a starting point for a software architecture where you can develop truly secure systems. And we list some of the properties for safety critical and security critical things. They need to be small, very simple, well tested, and isolated. In other words, they shouldn't depend on complex components in the system to do their job. And ultimately, if we look at, I mentioned IVI systems earlier, and this is something that we have deployed in tens of millions of cars today, production vehicles that are on the road, infotainment systems that run either Android or Linux to give you that complex software environment with all the multimedia support, that modern look and feel. A lot of people now are deploying Android so that they can have app stores and downloadable apps. And if you notice the diagram here, we have the Integrity RTOS at the bottom, and we can put those virtual machines running either Android or Linux with all that complexity, and it's completely isolated from other safety critical or security critical applications that run on top of that RTOS. Now, that RTOS is safety certified as an safety element out of context up to ASIL D, which is the highest level safety standard for automotive systems. And it's also been evaluated against the most rigorous security policies in the world. So we believe that this is the approach. This is how you can get there so that you can have a truly safe, truly secure system with small, simple components running on the same system that hosts these very complex components.
Can you also give us some examples where you employ your technology?
Well,
inside
yes.
the car.
Yeah, I mean, in the car. Yeah, sure. We are in tens of millions of digital instrument clusters running like ASIL B telltales
across different brands.
Across many different brands. Many of the OEMs don't let us say who they are, and so I'm not going to take any chances on the video, but major European brands, major American brands, also in Japan. This year at the Consumer Electronics Show, we did have a big customer of ours, General Motors, that allowed us to talk about, in fact, this specific type environment that we worked with them on. For the model year 2020, we had a Cadillac XTS in our booth, but it's in the Silverado, it's in many of their production vehicles, where we're deploying this architecture in their infotainment system. So it is the multi-visor virtual machine manager with an Android-based OS for providing the infotainment, and then Integrity is hosting some of the safety critical things. So in that system, there are safety critical chimes, there is a rear view camera, as well as the tracking lines, and then also the management of the vehicle interface is all handled by Integrity in that system.
Which role does standardization play in this context? Because this seems like a proprietary solution from you.
Well, there are aspects of this solution that are proprietary. I mean, the API for Integrity is a proprietary API, but we also have layers of abstraction on top of that API that do support like full POSIX standards. We're working with the Adaptive AUTOSAR committee right now to bring Adaptive AUTOSAR to integrity. So we do embrace standards, and we realize those are an important part of the automotive ecosystem, and that is something that we're working with today.
Are you standardizing in both AUTOSAR Adaptive and AUTOSAR Classic?
So we have different approaches for adaptive and classic. We have already today partnerships with companies like Vector and Electrobit and Tata for their AUTOSAR products. And if we look again at this diagram, we can actually deploy those AUTOSAR runtime environments as a virtual address space. It's not listed on my diagram here, but as one of these green boxes, for example.
That's one of the columns.
We could deploy a Vector or an Electrobit classic AUTOSAR, and the OS API translation, we translate directly to native integrity APIs. So that's something that can be done today. And then as far as the adaptive AUTOSAR, mainly the OS interface for that is the POSIX interface. And so we are working with that consortium as well.
Okay. Thank you very much, Joe.
Yeah.
It was an inspiring talk. Thank you very much.
Thank you for having me.
For coming by, for stopping by.
Yeah.
And take care.
Okay.
Have a good show.
Thank you. Bye-bye.
Thank you.